Good morning, everyone. Thank you for your patience. We're ready to start this talk now. First, I'd like to remind you of the chat, where you can just put all your thoughts in, and the Ask a Question button, which is on the bottom of the screen. When you have any questions, just write it in there, but please indicate with a plus or a minus whether you'd like to be invited on screen to ask the question yourself or not. And if you don't want to, then I just ask the question for you. Remember, this whole session is being recorded. The questions are recorded as well. So if you come on screen, you consent to being recorded, just so that you're aware of that. So with that basic administrative information, I'm very happy today to introduce our speaker for the second speaker of our emerging techniques session. I'm going to mispronounce your name. I'm really sorry.
No, it's okay. It's okay. I can do it.
So Eirini, I'm just going to
Eirini Papagiakoumou.
Exactly. She's basically been working on manipulating light and using all its properties in microscopy methods to study many different interesting things, basically throughout her whole scientific career already. And currently she's working at the Wavefront Engineering Microscopy Group at the Vision Institute in Paris, using all these different light shaping methods that she'll talk about, while maintaining really good spatial resolution. So it's a very interesting technical challenge that I think we can all learn a lot from. So with that, let's start this talk.
Okay, good morning, everybody. Thank you for virtually attending my talk, and sorry for the small delay. I had some technical problems. Hopefully, we won't have them in the rest of the presentation. So I thank also the organizers. It's the second time I joined the Neurizons panel. The first was in 2013, I think, and it was a very nice experience. Today I'm going to talk to you about methods we use in our lab at the Vision Institute in Paris for sculpting light in order to stimulate neurons. And before I start, I would like to thank my collaborators at the Wavefront Engineering Microscopy Group, which is headed by Valentina Imbriani. And I thank them because you will see in this presentation some work that they have developed for the methods that they have developed, and many of the images that you will see are contributed by them. So let's start. So I would like just to briefly remind you that the use of light in modern neuroscience as a tool for reading, or during also the last 15 years as a tool to stimulate or writing neuronal activity, has revolutionized the field by changing the way that neurophysiology experiments are conducted. So having acquired important knowledge on how neurons work individually, mainly by studies using electrical stimulation and recordings on single cells, neuroscientists now, they wish to understand how neurons interact within a circuit, and eventually how circuits interact between them within the brain. And all this with the appropriate temporal precision, especially in the case of writing neuronal activity, which should be of the order of a few milliseconds, both for spike jitter and temporal resolution. That is, spike jitter is the time precision that we are able to evoke action potentials with repetitive light stimulations. And by temporal resolution, we mean which is the maximum spiking frequency rate that we can achieve with our optical methods. And all this in order to be able to reproduce different activity patterns in neurons in order to being able to replay neuronal activity. The ultimate goal for all this is to reach one day the level of globally understanding the brain function and find new ways to treat, cure, and eventually prevent brain disorders. So the development and application of innovative technologies in optical microscopy, together with the continuously improved toolbox of molecular probes, sensors, and actuators that are sensitive to light, have enabled studies where interrogation of neuronal circuits happens in an all-optical way, and has allowed researchers to show how individual cells and complex neuronal circuits interact in both time and space dynamically. Manipulation of neurons is mainly done via optogenetics. Other methods also exist, like uncaging, but here I will talk only about optogenetics today. And for monitoring the neuronal responses, we usually use calcium or voltage imaging. Voltage imaging, it gets more and more popular lately because of new efficient probes that have come into stage. Here I'm going to insist on optical technologies, and optical technologies in particular dedicate in spatially and or temporally manipulating the light beam entering a microscope in order to achieve a rapid, specific spatiotemporal illumination of a large, of the largest possible volume at the sample. The easiest way to illuminate a large population of neurons is to send light to the brain via an optical fiber. And this is convenient because it allows relatively easily to perform in vivo experiments in freely moving animals. And also by combining miniaturized microscopes with optrodes, we can also record electrical neuronal activity with via electrodes, and that provides high temporal precision for the recording activity. The lack of spatial specificity of the illumination in that case is counterbalanced by the genetic specificity of targeting the opsins to specific neuron types, and the recruitment of entire circuits is enabled by the low excitation level of opsins, which is the usual case at visible light. Nevertheless, improving the spatial selectivity of the excitation can be substantial for some kind of studies, like studies concerning mapping of functional connectivity, or establishing the critical number of neurons or specific spatiotemporal excitation patterns that may control the function of a circuit, or even producing asynchronous patterns. So for all this, we need more sophisticated illumination methods. And here it was noticing, okay, that as far as spatial selectivity is concerned, this we can also achieve it by molecular focusing, that is by using soma-restricted opsins. And in that case, we avoid, we can, as you can see here, we can suppress or totally eliminate spurious excitation of neighboring neurons to our target neuron by activating their dendrites or axons, so their processes that cross the illumination volume. However, molecular focusing is not enough when we use wide field excitation approaches, because in any case, we excite unselectively the whole network. So the ideal illumination method should satisfy the following challenges: should provide micrometric spatial resolution, should be robust to scattering in order to be able to penetrate in depth for applications that require that. Should provide multi-scale light excitation in 3 dimensions, give temporal, having a good temporal precision, as I already said, and being proper for being combined in all optical studies. So for the first two, to satisfy the first two, we use 2-photon excitation, okay? Because that inherently gives optical sectioning and thus improved axial resolution compared to 1-photon excitation, and it gives robustness to scattering thanks to the longer excitation wavelength. 3-photon excitation is lately coming into stage as well for reaching even deeper brain regions than with 2-photon excitation. The methods that have been used so far, I'm always talking about 2-photon excitation now because 3-photon excitation is not so so common with the techniques that I'm going to talk to you. So the methods that have been used so far, they can be globally summarized in 2 large categories: the serial methods, where the cells to be excited are fast scanned by a focused laser spot, and the parallel methods, where the cells are illuminated simultaneously with spatially shaped patterns of light. Scanning methods traditionally use spiral trajectories to scan the laser spot over the cell soma. as this has been suggested as the most efficient way of scanning around the cell for recruiting the channels in the more suitable way to trigger action potentials, and that was back in 2009. Raster scanning has been also reported in few works, but now the most commonly done is spiral scanning. And however, the main problem of laser scanning methods used for neural activation is their limited temporal resolution, so the time that it takes to scan over the neuron. And especially this is critical when it comes to multiple cell stimulation, where scanning has to be over the cell soma plus from one cell to the other. Actually, it becomes impossible to successfully activate more than 2-3 cells in this way, and even more when the cells are in different axial planes. The problem of the temporal resolution is overcome with the use of parallel methods, where the only limited parameter in terms of temporal resolution in that case is the dwell time of the actuator itself. And parallel methods can be used in 2 or 3 dimensions without problem in terms of temporal resolution. However, they are limited in terms of necessary power, as they illuminate large regions at the sample if we want to illuminate a large number of neurons. So intermediate solutions have been proposed, where the laser beam is first multiplexed in space by a parallel method like computer-generated holography. And then the different beamlets are scanned in spiral trajectories over the cell somata that we target. And in that case, the temporal resolution is improved compared to pure scanning methods, okay, because we don't scan from one neuron to the other. And there's no the power limitation, because here we use diffraction limited spots or near diffraction limited spots to activate the neuron. I mean, there are always power limitations, but they are not so critical as in parallel illumination methods. Now, we have seen also one study where they used low numerical aperture Gaussian beams to cover the whole neuron, and then they scanned the beam from one side to the other. But this is also limited in terms of temporal resolution, because it turns out that the time we need to scan from one location to the other is more critical than the time we need to scan in the spiral trajectory over the neuron. In fact, this now it can be done in few milliseconds in the more recent studies. So now, after 11 years of 2-photon optogenetic activation, the 2 approaches that predominated the field are either pure parallel or scanning parallel approaches using computer-generated holography. And in any case, as you can understand, the key method is the use of computer-generated holography, and this is where my lab specializes and where I'm going to focus in the rest of my talk. So computer-generated holography is based on phase modulation of the electric field of the input beam. And phase modulation is exactly what happens, for instance, when you use a lens to curve the beam's wavefront in order to focus it in a spot. Now imagine that instead of having a lens to curve the wavefront, you have a material with a gradient of the refractive index from the borders to the center. Because the speed of light gets smaller in the areas with bigger refractive index, the output wavefront can be curved exactly in the same way for focusing the beam in a small spot. And now imagine that instead of having just a piece of material, you have a matrix array with thousands of pixels, where the refractive index can change locally to each of them. And this can be done, for instance, with liquid crystal arrays, where the refractive index can change by controlling the orientation of the liquid crystal by applying a certain amount of voltage in each pixel. So these devices exist, and they are called liquid crystal-based special light modulators, or simply SLMs. And the phase modulation we can achieve in that case can be really arbitrary and can lead to the projection of different light intensity configurations like 3D beamlets or arbitrary excitation patterns. Now, how do we define the phase modulation, the phase map? So to define the local change of the refractive index in each pixel, and thus the delay that will be applied in each part of the beam modulate the whole wavefront, we use iterative Fourier transform algorithms. And in that case, given a specific desired intensity distribution at the image plane, the algorithm performs the inverse Fourier transform the inverse Fourier transform calculation to estimate the phase of the electric field at the back focal plane of the objective that would generate the desired pattern at the focal plane of the objective. After a few iterations back and forward from the image plane to the back focal plane and back to the image plane again, the algorithm converges at some point and generates a phase map encoded with gray levels from 0 to 2p. And that is next encoded to voltage and addressed to the liquid crystal special light modulator according to its lookup table, to the device's lookup table. After the beam is modulated on the SLM, a computer-generated hologram of the laser beam appears at the image plane. So computer-generated holography can be used in 1 or 2 photon excitation or 3 photon excitation, in generally on multi-photon excitation. And here I show you some examples of different kind of patterns in 2 or 3 dimensions. We can tune the size of the spot, mimic different subcellular processes, project arbitrary excitation patterns in 3D, or diffract or small beamlets in 3D diffraction limited spots, and that's the modality that is used in scanning parallel approaches. But we will see this also in the following. And interestingly, we can also project patterns and light distributions that can change dynamically by sequential projection of phase holograms. So an interesting characteristic of computer-generated holograms is the enhanced axial resolution compared to other beams of the same size, like low numerical aperture Gaussian beams. And this is the result of the design of computer-generated holography systems where the beam fills the back aperture of the objective independently of the size of the intensity pattern at the image plane. However, even in 2 photon excitation, where the axial resolution is supposed to be optimum, it quickly deteriorates with the increase in the excitation surface, as it is the case, for instance, when we want to excite a dense cell distribution. You see, we can go from, in our setup, with the characteristics of our setup, we want, for instance, in this example, from 15 micrometers to 40 for a dense cell, mimicking a dense cell distribution. So is there a way to get large excitation areas with high axial resolution and better optical sectioning? Well, if I ask the question, it means that the answer is yes, and that's by using temporal focusing. So as you know, 2 photon excitation has a quadratic dependence on light intensity or otherwise on photon density. So when we use special focusing for achieving 2 photon excitation, what happens is that an optical lens, an optical lens achieves optical confinement by generating an actual spatial gradient in photon density. Okay, so in temporal focusing, we take advantage of the dependence of the 2 photon excitation signal on time, so in the inverse pulse duration, and we create a time lens that achieves optical confinement by generating an axial temporal gradient, this time in photon density. In other words, the pulse duration is modified along the axial position, and fluorescence is excited only where the pulse is short enough, that is in the vicinity of the focal plane. And here is where we have the temporal focus. But how can we create a time lens experimentally? So there are several ways, but most commonly now it's done by using a diffraction grating in the optical path that diffracts the different spectral frequencies of the femtosecond laser pulses at different angles. Each spectral frequency follows a slightly different optical path through the telescope of a lens and the objective. Okay, the telescope is comprised by these 2 lenses. And recombining those spectral frequencies after the objective gives a position-dependent pulse broadening This means that the frequencies that they reach the out of focus planes, they arrive with a certain delay, and thus they give broadened pulses, while the different frequencies arrive in phase only at the focal plane. And so they recombine perfectly, and this is where we have the temporal focus. Okay. The depth of the temporal focus, or in other words, the axial resolution that we can achieve of the excited fluorescence, depends on how we design the system optically, namely the magnification of the telescope that we use, the numerical aperture of the objective, the illumination angle of the grating here, because by increasing the illumination angle, we further increase the differences in the optical paths between the spectral frequencies. And if we satisfy this condition here, then the best we can get for wide field temporal focusing is we get an axial resolution that is equivalent to the one of line scanning 2-photon excitation microscopy. And how does this translate in numbers? Well, if we use temporal focusing to generate a large Gaussian beam for covering a whole cell surface, for instance, this is how it looks like, the illumination of the back aperture of the objective. You see the grating disperses all the frequencies, and S is the size of the monochromatic, of each monochromatic, let's say, beam. And here is the 2-photon excitation signal in different planes, and this is how it changes by performing the change in the modification in the pulse duration. And then temporal focusing would help to confine the excitation volume from hundreds of microns, that would be the case for a low numerical aperture Gaussian beams, down to a few micrometers. And then I will show you also an example by using computer-generated holography in combination with temporal focusing. In that case, the grating is put at the output plane of computer-generated holography method. So let's say at an image plane that is then conjugated to the focal plane with a telescope of the lens and the objective that is also used for temporal focusing. So in that case, you see, in the example I showed you before, we were able to get the axial resolution down to less than 10 micrometers for both single cell excitation or dense cell excitation configurations. So in the next few slides, I will show you some results obtained with temporally focused computer-generated holography in neuronal photoactivation of layer 2-3 neurons of the visual cortex in our lab in vivo. And so to test the temporal capabilities of our method, we have induced light-driven spiking in neurons expressing different options of different kinetics, slow, medium, or faster. And that we did with, we perform a holographic activation with a single 12 micrometer diameter spot. You can see the details here. And in all cases, both for slow or fast kinetic options, so we observed, here's the action potential probability. We observed the millisecond time, millisecond spike latency and sub-millisecond spike jitter, especially for the faster options like COCHR and Crimson R. So we have also tested the spatial selectivity of photoactivation by targeting multiple cells in groups of 5 to 8 cells in the preparations expressing the opsin RICHR and recording the activity by calcium imaging of GCAM6. And in general, we have observed that calcium responses were specific to targeted cells, but sometimes also in non-targeted cells. So upon illumination at the highest tested intensity here, as you can see, as an example, non-targeted cells had an activation probability of less than 50% when they were at about 40 to 50 micrometers from the target neuron. This distance is still farther than that for single cell activation, which was about 7 micrometers in the specific experiment. And this can be attributed first to activation of neurites from the non-target cells near the target cells by defocused light. And second, to postsynaptic activation of non-target cells by connections to multiple activated target cells. So because here we didn't use a soma-targeted opsin, so the use of a soma-targeted opsin would help to eliminate this type of undesired activation. Finally, here I'm showing you another example with faster opsin for the selectivity of holographic activation during all optical in vivo control of neuronal activity. So here we have a somatic opsin, a somatic COCHR, and you see on the top, you see that we activate the 3 cells that they are really close together. And you see the responses on the 3 cells, and on the bottom we have removed 2 spots. And you see that responses vanish from the 2 cells where we have removed the spot. So this is another example. So far I have talked to you about excitation in 2 dimensions. However, brain has a 3D structure, as you know, and I've already told you that with computer-generated holography we can project spots in different planes. So how can we do that? Well, this is simply done by adding a lens phase modulation to the phase profile that generates the 2D hologram. This is the lens phase modulation. And this can displace a pattern, whatever is diffraction limited spots or arbitrary pattern, axially, okay, out from the focal plane. However, when we use temporal focusing, things are not so straightforward, because when we put the grating for performing temporal focusing, then we have to project all the. I'm waiting for the animation. So we need to project all the patterns at a single plane. Otherwise, the 2-photon excitation at the sample will be suppressed by temporal focusing. That's the goal for using temporal focusing. However, what we want is then we get back, if we do so, we get back all the spots at the focal plane of the objective. So how can we separate the spots again in the different axial planes? Well, this can be done by using a second special light modulator at the Fourier plane after the grating. And by addressing this second special light modulator with different lens effects for the different shapes, we can again displace the patterns to different planes. In this way, all patterns will be temporally focused. Now, for the projection of different patterns in different planes, the 2 SLMs need to be addressed in independent regions for each pattern. The first SLM encoding the different 2D shapes that we want to produce, to project, and the second SLM encoding for the axial displacement. This is okay when we have a few shapes to project, but it becomes cumbersome when we need to project tens or even hundreds of spots for circuit studies. In that case, so here you see how the lateral, the axial projection of patterns, and you see that both patterns are temporally focused, okay? So when we want to project tens or hundreds of spots for performing circuit studies, what we usually need is to use the same spot size, okay? Thus, an alternative way for using the above system is to generate a single pattern with the first SLM that we multiplex next with the second SLM in 3 dimensions. By using in 3 dimensions, by using the second SLM in the 3D diffraction limited mode, as I showed you before. So convolution of the 2 patterns, of the 2D pattern and of the 3D pattern, generates multiple replicas at the sample plane, in fact at the sample volume. And this is not limited by dividing the SLM in different regions. So in principle, the only limit in that case is for the number of spots that we project is the power we have, the power budget, and of course the fact not to generate too much heat in the preparation. Note that temporal focusing is absolutely necessary in that case if we want to preserve a single cell resolution. Otherwise, we get excitation everywhere in the volume. And actually, the latter system is quite flexible because we can replace the first beam shaping unit with any shaping modality that fits better our application. Thus, besides computer-generated holography that I showed you in the previous cases, one can use simply low numerical aperture Gaussian beams that are first temporally focused and then specially multiplexed in 3 dimensions by the second SLM. This is actually more commonly known in the literature by the name of 3D shot, the method presented by the Desnik lab. Or we can even perform a complex amplitude and phase modulation on the first SLM for the projection of speckle-free patterns. So this is a little bit more complicated to explain, but if you want, I can give you more details at the end of the talk. So finally, we tested that multiplex temporally focused computer-generated holography works good also through green lenses for neuronal photoactivation in depth. So as you can see here, the axial resolution of the excitation spots is strongly affected by the green lens. In fact, it's worse than in the previous slide. And that's why the use of temporal focusing here is also critical. For instance, here we were getting, when we did this experiment without the use of temporal focusing, we were getting 70 micrometers of full width at half maximum for the axial resolution of 15 micrometers holographic spots. And with temporal focusing, we go down to 20 micrometers. So performing a similar all-optical experiment as the one I showed you before, we were able to photoactivate neurons through the green lens and record the calcium responses. And here you see the example. The option here is again VCHAR. And for the comparison, you see that the selectivity of the activation for single cell and multi-cell activation. And you see again here that in the second case here, we show only relatively to depth. Of course, it gets worse as we go deeper. But you see that the distance in which we have a 50% action potential probability for exciting for that the cell is a neighboring cell to the target neuron is excited is again of the order of 50 micrometers. So it's comparable with the case when we don't use the green lens. So I will stop here because now I don't know if how much time I have, but I hope you had a useful overview of the methods we have been developing all of these years in our group. Of course, it was fast, so I'll be happy to answer your questions. And before closing, just because I didn't have the time to insist more on specific biological applications, I would like to give you some hints for discovering further what these kind of methods can do. And these are two examples where computer-generated holography has been used in scanning parallel approaches with spiral trajectories. One example is from the UST lab and the other from the Daseroth lab. And they are used to identify the neuronal representation of a behaviorally potent percept. And with this, I would like to thank you for watching.
Thank you very much. That was a very interesting talk. There's so much more possible than I realized there was. We actually have a few very interesting questions. So let's go to them. The first one, actually, I'll invite the user Bamer on screen so he can ask the question himself. Let's see. Yes, he's connecting, so let's give it a second. Okay.
Hello.
Hi.
Good morning.
Good morning.
Thank you for this great talk. I enjoyed this a lot, especially for these nice drawings with computer-generated holograms. I have a more technical background, so I was not sure if these questions touch all of the interests of the audience. But you just interrupt me and say, stop, then it's okay for me. I was wondering, I did my diploma work in computer-generated holograms by myself. And one critical thing is to calculate these phase matrices for the spatial light modulator, the diffractive optical elements. So you have to optimize the phase for this 3D stimulation. And did you play around with different optimizers for that purpose?
You mean in terms of algorithms that we used?
Yes, exactly.
Yeah. So for which of them? Yes, we did play around. It's not so so plug and play.
Yes.
Let's say, but the most critical is when you want to project. Sorry, I will go back if I don't know if I go out from the slideshow presentation. I don't know if it is going to work. Anyway, I don't do that. So in fact, we had to work in optimizing the algorithm, mostly in the case of 3D 3D projection of arbitrary excitation patterns. So yeah, now the slide it's back. So and the most critical thing is that you, especially for neuronal activation, is that you need to be sure that that the intensity that you send to your spots is homogenized, so that you excite the neurons in a similar way in your excitation field. And this is more difficult when you do it in 3 dimensions, because you need to take into account in fact, the factor that I didn't talk about here, because, but probably you know, because you are in the field. So the limiting factor in this case is the diffraction efficiency of the SLM. Okay, so this means that the light is not diffracted in the same way in X, Y, and in Z. And this gives inhomogeneities in the intensity, and this has to be taken into account when you apply your algorithm. So in fact, they are weighted algorithms that for diffraction limited spots, it was already published. It was working very nicely. For this case, where we did the projection of 3D arbitrary excitation patterns, it was more complicated. But I had a very talented PhD student who did this very nicely. And in fact, it's possible. You do a pre-calibration of the system and you compensate for the pattern excitation intensity. But in both cases, for axial projection of patterns, let's say, we used the same algorithm. Okay, it's just that here what we did in this case, more than in that case, because it's more critical here, is that we also took into account, we performed a single spot projection plane after plane, and we calibrated the system, and we took into account this calibration later for adjusting the weight factor in the algorithm depending on the axial plane.
That makes sense. Yes. So you have an iterative approach for counting all of the drawbacks of the system, or the characteristics of the system. This is very, very intelligent to do so. I have also.
Sorry, I would like to. So the compensation of the diffraction efficiency in that it can also be done post processing. I mean, after the calculation of the algorithm. It depends, but I mean, the algorithms. There are algorithms that they do take into account the weight according to the position of the spot, but they take it into account only theoretically. And in the experiment, sometimes you have more factors, aberrations that change that. So we can do both. We can we can interact in the algorithm, and we can also correct after the calculation, post calculation of the phase profile.
One thing that also comes when I was doing literature research on that is the refreshing rate of the spatial light modulator, how fast you can be, because there are several companies which are quite limited to the video rate, like 60 hertz or something, but you want to go higher. So I know different companies, and at which refreshing rate you are.
Here we just used the 60 hertz. We just, because we stayed with SLMs that we have tested and we knew before. It's true now there are companies that they suggest models that can go very high. but we haven't tested that, and for our applications, it still works fine. Well, I showed you the example with the man walking, so
yes.
that was fast enough for us if we
Yes,
wanted to project.
yes. I mean, you would need it then if you go to more neurons and thicker stacks, and so you would need a higher refreshing rate. But but the problem is that's going also to the costs, and that's related to the next question. The safe fire. Just one question.
Okay, one short one, and then we really have to.
The laser is very expensive for the femtosecond pulses. Is there a way to reduce the cost for the laser?
That is you need to ask the laser company. Yeah, I mean, this depends on how. Now, I think with the photon
is there another laser than the Taisei laser for femtosecond?
Now there well, it becomes relatively cheap, but lasers are always expensive. These kind of systems, but they are the interbeam-based, interbeam doped fiber amplifier systems. That they emit around 1030, 1040 nanometers, and these, I mean, we are doing the experiments with these kind of lasers. They are still expensive, but since now 3-photon excitation comes more and more into stage, I think the 3-photon excitation systems will become more and more expensive, and the 2-photon price for the 2-photon lasers will go a little bit down. But
thank you for your answers. This was very technical, so thank you.
You're welcome.
Thank you very much for the interesting questions, and I want to thank you again for this very interesting talk. I think all of us learned a lot today. Unfortunately, due to time, we're going to have to end it here. I'm sure if people have other specific questions, they can probably reach out to you and have a discussion.
Yeah, sure.
Thank you very much, and see you in the next talk.
Bye-bye.
Bye.
Thank you.